Question, when you finish drawing the structure, determine how many bonding pairs and how many lone pairs of electrons are associated with the central atom. The reason I asked that question is that that's the thing we're gonna look at when we predict shape. We look at what's around the central atom, and basically we ask ourselves, for example, in this case, we've got three bonding pairs and one lone pair. In three-dimensional space, what's the shape that allows those things to be as far away from each other as possible? In other words, minimizing the most force. That's what valence scale electron pair repulsion theory is all about. And you can almost get to those shapes. Right. If you take a bunch of balloons, blow them up, and put them together. That's the idea. Diagonal. Here's bottom page. Get there soon. Draw Lewis structure for molecule boron trifluoride. And remember, boron only has three valence electrons. You can only pair three, and therefore it can only get the benefit of three more, but it's a central atom. So boron trichloride, just like boron hydride. And it doesn't matter how you arrange the three, as long as now, when you count the valence electrons that you've used and compare them to how many you have left, you're short electrons. Boron needs two more. It can't get two more because there aren't two. But again, it's violating the octet rule only if it's a central atom. So boron, beryllium, and aluminum, the medical covalent compounds, they will be a central atom and the octet. But they'll never be a peripheral. Okay. So let's talk about significant things. You've seen that one valence electron pair between two basic covalent constitutes a single covalent bond. Every line we draw is an electron shared between two nuclei by adjacent atoms. There's also many cases where the atoms between the atoms involve more than one pair. So those two pairs are shared, you draw two lines. That's a double. Three pairs are shared, that's a triple. You draw three. But as far as I know, there is no such thing as a quadruple covalent bond. As you might expect, as multiple bonds involve more attractive forces between two atoms than single bonds do, multiple bonds are stronger. So the attractive force between more electrons between two nuclei is going to be over here two. There's going to be more, six going to be more. Bond strengths are usually measured by the amount of energy required to break a mole of those bonds. So you see here some bond energy comparisons from single, double, and triple bonds. The first six are between the same two elements. Carbon-carbon single bond, double and triple. Nitrogen, single, double, and triple. And then here's carbon single bonded oxygen, double, and triple. Now, if you look at these, I mean, the general trend is obvious. Double bonds are stronger than single, triple bonds are stronger than double. But you might notice something different about this triplet than this one. So, for example, a carbon-carbon double bond is stronger than a single, but it's not twice as strong as a single. Carbon triple bond is certainly stronger than a double, but it's certainly not 3 times stronger than a single, and 1.5 times stronger than a double. So in this case, there's got to be something working against that. And what it is not only the multiple bonds, not only are they stronger, but because the attractive forces are stronger, they're also shorter. So bond length goes down as bond multiplicity goes up. And the shorter the bond, smaller region of space over which that increasing number of electrons exists. So there's going to be some electron repulsion. And even though to break, for example, a carbon-carbon triple takes more energy to fully separate those atoms from each other, a triple bond is more reactive than a double bond. Because there's more electron repulsion. It gets less energy if you want. The activation energy is less to start that bond break. A double bond is more reactive than a single bond. And get into organic chemistry, fingers crossed, we'll learn that whenever you have a carbons in a long chain molecule, if you've got a bunch of double bonds in there, those are the most reactive portions. And chemists have a name for that. We call it polyunsaturated form. And you probably heard that term before, but that's what it means, many multiple bonds. But then you look at nitrogen and things are a little different than nitrogen. Nitrogen double bond is more than twice as strong as a single bond. And a nitrogen triple bond is way more than 3 times stronger than a single bond. And it's more than double the strength or double. And that's a bit of a kind of, can you guess one potential reason for that? Well, as we go left to right, atoms get smaller, right? So nitrogen is a smaller atom than carbon. We could put smaller atoms closer together without as much electron-electron repulsion happening. But it also has to do with the other electrons that are in the scenario. So for example, carbon has 4 valence electrons, nitrogen has 5. And this is among the strongest atom-to-atom bond we know. And it's a good thing that that bond is that strong, because 80% of the air we breathe is this. And we don't want that reacting with oxygen in the air, because if it did, then every time it rained, it would rain nitric acid. So the only way that that bond can be broken is by lightning, volcanoes, or there's a species of bacterium, as you may or may not have heard about in Bio-11, called, you guys talked about nitrogen fixation. You know the name of the bacterium that's responsible for it, just with an R, Rhizobium? Root nodule, know that? That's how nitrogen gets in your body. You don't get nitrogen in your body because you get struck by lightning or get covered with lava. You get nitrogen in your body because nitrogen compounds because you eat it. And there's like bacteria, we don't know how they do it yet, but for some reason at atmospheric pressure and atmospheric temperature, they take N2 right out of the air, break that bond somehow, and put it into compounds. And then those are eaten by herbivores, we eat them, and that's where we get the nitrogen. So we can't fix nitrogen. We can't breathe air in and get that nitrogen in our bodies. Any idea what we need nitrogen for in our bodies? What are the 4 biomolecules? Heard of those? Carbohydrates, fats or lipids, proteins, and nucleic acids. Ever heard of those? Ever? This is frightening. The nucleic acid, like the oxyribonucleic acid, DNA. Remember that from grade 10? What sticks to what in that long twisted zipper? What connects to what? What do we call those things? Nice. I taught some of you last year. What are the components of a nucleotide? There's 3 things. Sugar, phosphate, that's the backbone. What's the third thing?
Nitrogen base.
Say the first word louder.
Nitrogen base.
Nitrogen base. Nitrogen is a component of the molecule of life. So the adenine and thymine that stick together, and the guanine and the cytosine that stick together, are nitrogen bases. And when they stick together, we call it a base pair. Were it not for that, there would be no DNA or RNA for that. Pick another biomolecule, protein. What is protein composed of? 2 words, both start with A.
Amino acid.
Amino acids, correct. When we do organic chem, we'll learn that the amino end of an amino acid has a nitrogen in it. And that nitrogen is how the acid end of another amino acid sticks to it. And whatever isn't water and bone is effectively protein. So the DNA needs a nitrogen to tell the body what proteins to make, and the protein make you who you are. Yeah, nitrogen's kind of important. Plus, every enzyme is a protein. And enzymes control all the reactions that make all this stuff. So you can't overestimate the importance of nitrogen. And yet, we breathe it in and breathe it out and can't do anything with it. Okay. Carbon, oxygen double, carbon, oxygen triple. We'll talk about how those things and these all come to pass in a molecule as we move through this. Let's follow the steps outlined above to draw the Lewis structure for a molecule that contains double bonds, such as carbon dioxide. Now let's pretend we didn't know it contained multiple bonds. Let's say we just happily went along. Okay, we'll count the valence electrons, we'll draw the skeleton, and we'll go from there. But when we do that, we immediately realize that our first attempt at a skeleton is to be modified. So here's the formula of CO2. Oxygen doesn't like to stick to itself. Carbon needs more electrons than oxygen. This is an AXN structure. So that suggests carbon is in the middle, correct? Number of valence electron, 4 plus 2 times 6. So we've got 16 valence electrons. And nothing in this pair of elements can violate the octet rule. Carbon can't have any more because it's a second period element. Oxygen can't have any more than 8 because it's a second period element. And neither can have fewer than. Okay. So the only skeleton that makes sense is this one. Okay. Construct the skeleton we've used 4. Got 12 left. So we go, okay, this needs 6 and that needs 6. That's 12 right away. How many more does the carbon need? We're 4 electrons short. If we know that we can't violate the octet rule for these elements, if we know they can't have any more than 8, then that means we got to start with a different skeleton. And by that, I mean, in the skeleton, we start to incorporate multiple bonds. And for every multiple bond we put in there, we get 2 closer to having agreement. So would everybody realize, as I went through that, everybody see why we would need 16? 6 and 6 is 12, and 4 is 16, right? So we're 4 short. So that means draw a different skeleton. Well, let's do it one at a time. Let's put a double bond there. Now that goes. Well, now we got 3 lines, so now we've used 6. We've only got 10 left, but how many do we need? Well, this oxygen still needs 6. This needs 4, because 2 and 2 is 4. So that's already 10. But this only needs 2, doesn't it? Because it's got 6. So now we're closer, but we're not there yet. So now the next question is, do we put the next multiple bond here? Or do we put the next multiple bond here? Well, one way we can guess or predict is remembering the guidelines for skeletons. How many bonds does oxygen like to have? Look at the guidelines for the skeletons. Step 2. Oxygen normally forms how many bonds? 2. So if we put that in here, then we're goofing that up twice. This one has 3, this one only has 1. So that makes most of the sense based on the guidelines. Now, at this point, I wanted to add something to this section that I eventually added to the later section. Sherry said, we'll put it in put that in AP. The guidelines make sense based on what all the experiments we've done shows, and you guys all know oxygen needs 2 electrons to be like near someone else. So that's why 2 bonds are there. But whenever you're up against two skeletons or two different skeletons that both look okay, that both satisfy the electrons needed and the electrons available. There's a way that chemists use to say, okay, this one we're going to throw out, this one we're going to keep, and it's called formal charge. And I might talk about it, depending on time. We've got full velocity, right? So I'll probably talk about formal charge, but I probably won't put it on a test. Okay? But it's really where the guidelines come from. So there's a different skeleton. Now we've used 8. So we've got 8 left. Let's see how many we need. Well, the carbon doesn't need any at all, right? It's already 5. This oxygen needs 4. That's oxygen needs 4. 8 left. 8 need. Now what do we do when we have, if we've got agreement here, as the steps suggest, pair up the electrons we need and put them starting with the first atom. So it doesn't matter if you put the dots like that or like that. It doesn't matter. As long as there are 2 pairs of electrons on each of the peripheral atoms. Yes. Now, have we satisfied every octet? Are all the electrons arranged in pairs? And the number of atoms in the molecule match, our diagram match the formula you had, yes. So 2, 4, 6, 8, 10, 12, 14, 15, 16. Now, and part of what's on the next page may kind of added, and I don't like it. But again, I have, by the time I got to this, I was kind of tired of writing, so I said, fine, we're going to put it in. So notice that 16 electrons are required, but only 12 electrons are available to complete the octet, and therefore lacking 4 electrons. This means that we must return to step 2, redraw the molecular skeleton such that we incorporate one multiple bond for each pair of electrons that we lack. And that means we need two multiple bonds. And the question is, do I do that or I do that? Although both skeletons above show carbon forming a total of 4 bonds, as oxygen normally forms 2, we would choose skeleton number 1. Okay, that's what I wanted to just leave it. But then Meg said, well, no, notice also the symmetry associated with the choice opposed to skeleton 2. Molecules will often possess a high degree of symmetry. If they do, it's a coincidence. They don't, this isn't adopted because of the symmetry. There's far better reasons for it. And there's a lot of molecules that are asymmetric. There isn't symmetry. So I don't really like that. It's a little too simplistic. It does play out in a lot of cases, but it's not the reason. Okay? I like to think of it, there is a reason that the symmetry is there. But the symmetry is not the reason the molecule is there. It's the other way around. So again, now we get to it. As a final step, we see all 16 valence electrons can account for the structure. The structure of this molecule can be understood by considering how the valence electrons present in each individual atom are reorganized. So there's the Lewis structure of carbon. Each oxygen, notice each oxygen has 2 unpaired electrons. If you take this and you turn it sideways and write it like that, those are the 2 electrons that are going to be shared with the oxygen. Those 2 electrons are there. Notice the only electrons involved in bonding are the electrons by themselves in each of the Lewis structures for the atoms. And that's the idea. And I don't really like this. That's more a 3-dimensional structure attempt, but I would prefer that just do this instead. I don't like lines. It's the only diagram I could find, but I don't like lines for peripheral atom electrons because they're lone pairs and they take up more room. Yeah. Now, I don't think I went into this, but Is carbon dioxide the only compound of carbon and oxygen that you guys are aware of? What's that?
Carbon monoxide.
Carbon monoxide. You can do the same stuff, but this is kind of a unique structure. And to show you that, I guess like the book, I'll use black for carbon, red for oxygen. So 4 plus 6 is 10 minutes. Skeleton's not that tricky. One line. We use 2. We got 8 left. We need 12. We need 6 here. 6 there. So we're 4 here. So that suggests 2 extra bonds. In other words, a triple. Okay. Let's do that. 6. We got 4 left. Well, carbon only needs 2. Oxygen only needs 2. All 10 valence electrons are accounted for. Both atoms are associated with the same number of electrons in the reaction together. 2 equals 6, 8, 2 equals 6, 8. And it looks fine, and it is correct. It's just that if you actually dissect those lines a little bit, let's maybe draw that a little bigger. And instead of lines, let's draw the electrons that have to be between those two. Carbon only has 4 valence electrons. We've used 2 of them. So there's only 2 more left. Oxygen has 6 valence. We've only used 2 of them. So there's 4 left. So that looks fine. Electron coming from each atom sharing between adjacent nuclei. But it's the third bond that's the difference. Both electrons in this triple bond are coming from the same atom. The chemists have a name for that. You don't need to know the name. It's called a dative or coordinate bond. But it's evidence, if you will. I like to think of it as evidence how important being like the nearest noble gas actually is. It's like going into business with a partner, and you both need each other because that's the venture capital you're going to use to get the business off of it. But one of the partners has 2/3 of the money, the other only has 1/3. So it's not equal sharing. But unless this guy is on board, nothing happens. So the only way that oxygen can get 2 more electrons is to share 6 of its valence electrons with another atom. And that bond is like oxygen. Okay, this isn't ideal, but if I don't do that, I don't get 8. I don't get these 2. And that's not all triple bonds are like that, but this one is. Okay. As long as we're here, you guys know why carbon monoxide kills you? Why it's not good for you? Put it that way. But I know if you breathe it in too much, you die, right? Any idea why? You start breathing, okay, yeah, but why? Yeah.
Because you can't transport oxygen to the body tissues.
Yeah. What I hate to keep asking these questions, but what protein in your blood transports oxygen? 4 syllables. Why is your blood red?
Of hemoglobin?
Hemoglobin. Correct. If a protein ends in globin, it's a globular protein. It means all the amino acids. So let's say this is there's hemoglobin, okay? Long chain of amino acids. And it's twisted and folded in a specific way. And at 4 places on that long twisted chain of amino acids, you have what's called heme groups, Heme. And they're kind of like little platforms in the hemoglobin. At the center of each, it's an iron atom. That's the thing that grabs oxygen. So when you breathe in, the oxygen goes into your lungs. The oxygen diffuses across the alveoli in your lungs. Have you heard of that word? No. On the other side of the alveoli are your blood vessels, where hemoglobin, the iron in the hemoglobin, grabs the oxygen that diffuses across the membrane of your lungs. So each of these iron grabs an oxygen. Okay? And when the hemoglobin is fully populated with oxygen, we call the thing oxyhemoglobin. And then it goes from the inner surface of your lungs back to your heart pumps it to the capillaries, and then the oxygen comes off. Iron drops the oxygen. And hemoglobin is an amazing molecule. When it gets to the lungs, bereft of oxygen, doesn't have oxygen, it really wants one. And as soon as one goes on there, it's like it knows it's in the lungs. The affinity for the other oxygen goes up. So the more you give it, the more it wants. Then it goes to the capillaries, and then but it drops off in oxygen. As soon as one comes off, it wants to give the other ones away even more. So it's an amazing molecule. And it has to keep doing that. It has to want to grab oxygens at your lungs, and it has to want to give them away in your tissues. The problem is if you're also breathing in carbon monoxide. So if you're breathing in carbon monoxide, there's a bond that forms between the carbon and the iron. So that's called an organometallic bond. And it's 100 times stronger than this bond. Moreover, the amount of energy released when that carbon monoxide goes on the iron is enough to change the structure of hemoglobin sufficiently that even if one of these is on an iron, the other irons don't want any at all. And if there are other oxygens on there already, if one of these goes on there, these don't want to come off. So every carbon monoxide that lands on a hemoglobin poisons that molecule. It can't do what it's supposed to do. So if you breathe in a low carbon monoxide, you don't even notice it. But if you're breathing in a lot, you start to get tired. You can't see it, you can't smell it, you can't taste it. You just get tired. It's because your hemoglobin is slowly being poisoned. Your body's still pumping blood, but the blood's not doing anything. So you start to get sleepy, you fall asleep, then your organs shut down, your brain's starved of oxygen, you die. So it's a not giving you a recipe for killing yourself, but it's a pretty efficient way. And in the wintertime, particularly in rural areas where power goes out and people have portable generators, the portable generators are usually powered by gasoline. And if they're not vented properly, then that exhaust is going into a home and people can die. Even if your regular furnace isn't vented properly, carbon monoxide is always produced when hydrocarbons are burned. Okay? Little personal note, not to ruin your morning, but my cousin killed himself this way. Yeah, put a vacuum motor and a tailpipe in his mom's car when she's out of town. Put it in the back window of the car, started the car and killed himself. Doesn't hurt, but and people that suffer from carbon monoxide poisoning, if they're not dead, they're likely to die if they have inhaled enough carbon monoxide. But some success has been accomplished by putting people in hyperbaric oxygen chambers and under high pressure, kind of force some of the carbon monoxide off the hemoglobin. But if too many have been poisoned, you're done. You're done. So anyway, here's a nice bright and happy story to start with. Yeah. That's one complicating factor. When you're short electrons, as long as the atoms involved can have more than one bond. For example, you couldn't have done that with a fluorine. Because fluorine can't have any more than one bond. You couldn't have done that with a hydrogen. But you could with oxygen, and carbon, and nitrogen, things like that. Okay. What about the complicating factor where instead of not having enough, we have too many? This one's way easier. Sometimes we discover that fewer electrons are available to complete the octets of the atoms of the molecule. Other times, we might encounter situations where there are more electrons are available. This normally results in expanded octets with the central atom. So any extra electrons, effectively, in a nutshell, you're just going to plunk onto the central atom at the very end as a pair. That's it, okay? Remember that an expanded octet, though, whether it's a central atom or not, is only possible for an atom if d orbital electrons are available. So if the central atom isn't a third period element, you can't have an expanded octet. You need the d sublevel available. Let's investigate this by drawing the Lewis structure for one of the few compounds involving noble gases, xenon tetrafluoride. The first noble gas compounds were synthesized at UTC, actually, in 1966, by the chemist named Neil Bartlett. What he did was he put the most reactive elements in, and he began with the biggest noble gas. Biggest because that means the electrons on the outside, the 8 of them, are held the least tightly. So he took a little atom that's really the most reactive element, and he reacted with the biggest noble gas because the idea is that those outer electrons are a little bit malleable. They're not held really tight. So the compound is xenon tetrafluoride. So let's just follow the steps. Then you'll see how easy this is. Xenon's got 8 valence electrons. It doesn't need it. But if it's got any bonds, it makes sense that it's going to have an expanded octet because it's already got it. So we have 8 plus 4 is 7. 28 plus 8 is 36. We got to account for all 36. 4A can't have any more than one bond. So it's pretty clear that xenon has to be the central atom. If it's structured for what's in we've used 8. So you've got 28 left. Well, how many do we need? Well, xenon didn't need any in the first place. But each fluorine needs 6. Okay. 6 times 4 is only 24. We got 24 needed. Well, as expected, we got extra. And because 4 bonds are around xenon that already had 8, it makes sense that the 4 extra electrons are going to be on that xenon. But let's take the 24 that we need and begin with fluorine and put those 3 recognizable pairs around the fluorine. And the 4 that we have left, put them anywhere on the central atom. You could put the 2 pairs there. You could put them there. You can put them there. You can put them there. It doesn't matter. There's no attempt to make this look good. When we go to section 6.6 or 6.5, we'll see that this is actually a square planar structure. But we'll get there soon enough. Okay. So it's the expanded octets is easy. As long as it's a central atom, and as long as that atom is a third period element, okay. We could never have an expanded octet, for example, on neon. If we didn't have room for it, it's a second period. Let's try this one. Drawing a Lewis structure containing a multiple. So this molecule is hydrogen cyanide in water. It becomes something called hydrocyanic acid. It's a gas. I put this as a sample problem because it's a little trickier because we've got 3 different atoms and not 2. So, but let's go through the steps. To construct the skeleton, Hydrogen can only have one bond, right? So it can't be in the room. Which of these two things needs the most electrons? Carbon or nitrogen? Carbon. Carbon's in group 14. It needs 4 more, nitrogen in group 15, it needs 3. So it makes more sense to put carbon in the middle because anything in the middle is going to be getting more electrons than anything in the periphery. Okay? How many valence electrons do you have? 1 plus 4 is 5 plus 5 is 10. Hydrogen never obeys the octet rule. It can only have one bond. But the most likely skeleton is this. To construct a skeleton, we used 4. There are 6 left. Many need. Hydrogen doesn't need any. Carbon needs how many? This is something you guys should be able to do quickly. Every line is 2 electrons. Carbon has a left 4 equals 4 more, right? Yeah. Range is nitrogen. You're gonna have to do this on the final exam, guys, so stay engaged. It's got 2, right? That line means this. Okay, so it's already associated with 2. It needs 6 more, correct? So carbon needs 4. Nitrogen needs 6. That's 10. So we're 4 short. That suggests multiple bonds, but we can't put multiple bonds here. The 2 extra bonds have to be here. Okay. So when there's disagreement between what we have and what we need, we got to do a new skeleton. So if we're 4 short, then we need 2 extra bonds, and every bond, multiple bond we add, we get 2 closer to agreement. So we should have agreement. We've used 8 to construct the skeleton, which means we have 2 left, but we only need 2. Carbon already has 2 for 8. Hydrogen doesn't need any. Nitrogen needs 2. So done. Okay. Make sense? Now, when you put this thing into water and it becomes an acid, what's the other ion in your table of ions that ends with "ide" besides hydroxide? Let's call it atomic. Starts with C. This is the cyanide anode. When you put this in water, to a slight extent, hydrogen comes off. There's cyanide. That is an anode. Okay. I use its electrons here. And this looks a lot like carbon monoxide, except it's got a negative charge, which means it's even more attractive to an iron. And that'll kill you too, except this one's better. This is better than carbon monoxide. Yeah.
Carbon only has 4.
It does, but in the original molecule, it's sharing one with hydrogen, right? When I throw this gas in water, hydrogen leaves its electron here. That's why we have the negative. So this electron came from hydrogen, and that's why we have a negative. So the hydrogen goes away as an ion without its electron, and you learn that in Chem 12. That is one of the definitions of an acid, but it leaves its electron on the thing. So now this has a negative charge. And this is a very efficient force. One of the things that is in Nazi concentration camps. The gas that came in. So it was ionized with concentrated acid, you get hydrogen cyanide gas. You can put a solution potassium cyanide, an aqueous solution. You could rub it on someone's skin and build up. You put it in an aerosol mist and spray it in their face and build up. Anyway, I would find other things which will be limited to that, but chemistry's fun, but it's also a little knowledge is a dangerous thing. Formaldehyde is used as a disinfectant, a bonding agent, we put it in bodies, and a component in many organic synthesis reactions. Draw the Lewis structure of the molecule of formaldehyde. Hint, carbon is a central atom. Here's the formula. UH3. And carbon is a central atom. Can't be hydrogen, right? And again, does it make sense? Carbon central and oxygen isn't. Carbon needs 4 electrons, oxygen only needs 2. So yeah, it does. How many valence electrons do we have? 4 plus 2 is 6 plus 6 is 12. And if we construct the skeleton such that carbon is the central atom, then that gives us hydrogens have to be free. Okay? They can't have 2 modifiers. So we could, for example, do this. And drawing it that way is identical to drawing it this way. It doesn't matter. It's the same thing. Okay. So to construct a skeleton, we've used how many? How are you guys taking from here? Yeah. Let's say this was a question of farming. Draw the Lewis structure for formaldehyde. Also known as methanol. Bring that in account. Take it from here. You look at the title of the practice problems, Lewis structures containing multiple bonds and expanded octets. This qualifies as the first of those. Get the money down.
Yeah. That's right. Move on for more. Off it out, but one full problem.
I'm sick of experience.
Hey, show me again. What's wrong with it? Literally leaks ice cream. There's no dots on it then? Carbon? Shut up, carbon. No, like no, wait, that's what it says.
That's 2, 2, 2, 4, 6, 8, 10, 12, 12.
Carbon does.
Resistant? I think
Yeah.
No. It's like that's 2, 4, 6, 8.
yeah, I was gonna say, yeah, you have to take off the one from oxygen.
Oh, carbon does.
Yeah, you just take one off from oxygen because now it's already.
Doesn't matter where the dots are or no. I'm just gonna put them on the angle.
Just put them on angle.
When you need carbon needs 2, oxygen needs 6, right? So we need 8. Sure. That's suggesting 1 over more. They can't go here. They only go here. So that new skeleton means we've used 8, not 6. 2, 4, 6, 8. And it means we don't have 6 left, we only have 4 left. But as it turned out, we only need 4, because carbon's already got 8. Oxygen needs 4 more because it's got 4. So 4 left, 4 needed, 0 short. Done. Pair the electrons up and put them where they're needed. So, for example, there. That work. This. Or you could do this. Doesn't matter as long as there are clearly 2 pairs of electrons. And we're going to see in section 6.5 that that's a flat triangle. Trying to get it clear. There's carbon monoxide, I already did for you. Bromine trifluoride is a very reactive and toxic liquid that exposed on contact with water and organic compounds. Draw the Lewis structure for the molecule of BRX2. Now, multiple bond here, multiple bond here. The other title in that set of practice problems is the expanded octets. Notice we've got nothing but halogens here. A halogen normally only wants to form 1 bond, but if it forms more than 1, it has to be bigger than fluorine because it's either stuck to a smaller halogen, or oxygen. So the skeleton here, because the formula is AXN, that's going to be the central atom. Okay, fluorine can't ever have more than 1 line coming from it, just like hydrogen can, for exactly the same reason. And if bromine only needs 1 more electron, but it's bonded to 3 fluorines, we would expect it's going to have an expanded octet. So we've got halogens, fluorine, so we got 28 electrons, 7 times 3. The only skeleton that makes sense. You can do it symmetric if you want. You don't have to. I usually do that, but you can do it like this, that. Construct the skeleton. We 6. We got 22 left. We need, well, each fluorine needs 6 more. Did everybody see that when I do that? Each fluorine needs 6 more. Each fluorine is associated with 2, 6, and 6, and 6. That's 18, right? This needs 2. So we only need 20. So we got 2 extra, which is not a problem. We're just going to float those at the very end on moment. So put the 20 that we need where they're needed. 1, 2, 3, 4, 6. Remember, we always start with the peripheral atoms. That's 18. Bromine still needs 2. Now, right now, bromine's got an octet, 2, 4, 6, 8, and each fluorine has. You still got 2 left. So, yeah, that's what you're on there. Don't put them here. Don't do that. That's just silly. But there, what there doesn't matter. Does it make sense that bromine has an extra 2 electrons? Yeah. Because it normally forms 1 bond, but it's got extra 2 electrons with these. And we're going to learn in section 6.5 that that molecule is in shaped. Yeah.
Fluorine on the bottom,
Bottom,
like recalculate my points, like,
that's just that's how I draw.
oh,
You could draw it like this if you wanted to. Or you could draw it like this. Or you could draw it like that. It doesn't matter. Again, the attempt here is not to make it look 3D. That's just to have it on it. But when we do 6.5, we even look at the central atom and say, okay, 3 bonded atoms, 2 lone pairs, NX3E2. Not there yet. Fast. Well, once again, imagine if you want here 8 people that are actually there. Hope you're having a fun time and your holiday this week. I don't really have a bunch of kids today. We got 13 teachers over there. I know. They're getting paid. Now, what haven't we done? We haven't done our answer. polyatomic ions, if you look at your table of ions, what do you notice about most of the polyatomic ions? Answer before you do. Many polyatomic ions contain non-metal atoms bonded covalently. So sulfur, nitrogen, phosphorus, chlorine, perchlorine, carbon. They're all non-metals. And if they're all non-metals, inside that thing with the charge, the bonding has to be covalent. It's just that we don't have the same number of protons and electrons. So we should be able to draw Lewis structures for shared electrons in a polyatomic ion in the same way we draw it for neutral molecules. The only thing we have to remember is if something's got a charge, the number of electrons isn't the same as if it has no charge. So if we're drawing a polyatomic ion with a 1+ charge, when we add all the electrons up, we got to take one electron away. If we're making a Lewis structure for a negative ion, however, whatever the thing is with a negative charge, that's how many electrons we have to add. And it's usually pretty easy to remember because sometimes if you forget it, you got an odd number of electrons, which means something's wrong. So one of the simplest examples of that is ammonia, NH4+. So it's done for you in the book, but let's go through it. Now let's say we forget about that positive charge. So we change up down the electrons. Step 1. 5 with a nitrogen plus 421. And gives us 9. Something's wrong. Well, that's because that plus sign means we take an electron. So before we get what it equals, -1. And some of you forgot this in the orbital diagram. If it's a positive ion, the magnitude of the positive charge is how many electrons you take away. Not how many, the +2 or 2+ doesn't mean you add 2 electrons, it means you take them away. And an anion, the magnitude of the negative charge is how many electrons. Example of that is that. To construct the skeleton, hydrogen can only have one bond, nitrogen has to be in the middle. So the only skeleton we can draw is this. And to remind ourselves it's an ion, just like we do for Lewis structures for single atom ions. We wrap it in square brackets, then we put the charge. Okay. How many electrons to construct the skeleton? We have 4 lines with that's 8 electrons, right? And we have 8 valence electrons. We've used 8. We've got none left. Which is good, but we don't need it. Hydrogen's already got 2. Nitrogen is. So in this Lewis structure, there are no dots. Sometimes the case. Now it suggests, looking at it, that it's a flat structure. It's not. But again, that's what we'll do in section 6.5. That's probably as simple as it gets. When you thought everything is cool and there's no surprises, let's look at the next one. Serious case of resonance. What we've done, and what we always do with Lewis structures, is temporarily suspend our understanding of what electrons really are. They're not little dots. They're not motionless. They're negatively charged probability clouds. Okay. So this is convenient, but sometimes electrons are not as cooperative as we would like them to be. And even when the numbers work, there's still something that's doesn't seem to be right. The curious case of resonance. When a molecule or ion contains double bonds next to single bonds. So in other words, we got an atom with a central atom, say with a couple single bonds, double bonds, or maybe we got a single bond, atom, double bond. Whenever you have that, there are often different and equally correct Lewis structures that we can draw. Consider the case of the carbonate anion. So, let's pretend we're just gonna follow the steps. So there's a negative anion, polyatomic ion. Let's draw the carbonate anion. Bonding inside, it has to be covalent. Because there's nothing like non. So let's go through the steps. Number of valence electrons, 4 plus 3 times 6 plus 2. 18 and 4 is 22 plus 2 is 24 valence. Okay. Oxygen doesn't like to stick to itself. The molecule is of the form AXN. Carbon needs more electrons than oxygen. Lower family number, lower electronegativity, carbon's the central atom. So let's scale. Okay. And it's an ion. So can't forget this. Okay. How many electrons are used to construct the skeleton? How many lines do we have? How many electrons? 6. So we've got 18 left. How many do we need? Well, each oxygen needs 6, that's already 18. Carbon needs 2. 18 left, 20 need. So 1 too short. To which you would reply, that's not a problem, Mr. Toll, because that means we need a multiple bonds. So let's put the double bond here. And I'm using a different color for the. Now we go back and we redo our little electron bookkeeping thing. In that new skeleton, I've used 8. I've only got 16 left. How many do I need? Well, each two oxygens still need 6 each, so that's 12. This oxygen only needs 4, right? Because it's already got 4. The total for 16. Carbon doesn't need anything. Carbon's fine. So 16 less, 16 needed. Think we're done. Take the 16 that were needed. It's obvious it's a step that a lot of people forget. When they're building multiple bonds, as soon as they get agreement, they go, oh, you got to put these where they're needed. You got to account for all of these electrons. So we start with the first two atoms. 1, 2, 3, 4. 1, 2, 3, 4. This one's only 4. So let's count all those and make sure they work. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm done. You think, okay, I'm finished. It looks fine. But if you go back to page 322, you see the bottom that put there, carbon oxygen single bond, carbon oxygen double, carbon oxygen triple. We have very sophisticated and accurate and precise ways of measuring bond strength and bond length. So if this is the true picture of the carbonate atom, 2 of the bonds should be longer, 1 of the bonds should be shorter. These 2 bonds should be weaker, this bond should be stronger. When we look at the data, when we look at the carbonate atom and measure the bond length and the bond strength, all the bonds are identical. We don't have a double bond. We don't have any single bonds. All the bonds are a little shorter than a single, but a little longer than a double. They're a little stronger than a single, but not quite as strong as a double. It's as if that pair of electrons is kind of thrown into the structure and averaged among the three pairs of atoms. The chemists have a name for that. They call it delocalized electrons. The Lewis structures can't represent those. Now, is that weird in terms of electron behavior? Not really. Because remember, it's a probability cloud. Another way of saying it is those extra two electrons can be found equally between all the pairs of atoms. That pair, that pair, that pair. So how do we do it? Well, we can't with the Lewis structure. There's no one structure in a Lewis diagram that can represent delocalized electrons. So we invent a word, a label called resonance, which the idea is it's as if these pair of electrons resonate in the ion, switching places, if you will. Okay. And I don't like the diagram in here. Again, I wanted to add something to this, but this is the idea. That extra pair of electrons can resonate between this one and then this one. And then also between that pair and this pair. But you can look at that diagram and say, well, wait a minute. Let's identify each of those oxygens as different oxygens. Let's color that color and this color. The way the diagrams are drawn, you can just say, well, why don't you just turn them all? So if you just take that and turn it, then you now have this. So if you just turn that counterclockwise, you get this. It's the same thing, same double bonds of the same atom. And then turn it again. Then you'd have that one there, and you'd have this one here. The double bond would still be between that carbon and that oxygen. So that's not really enough. That's what Megan Sherry decided was enough. But you could say, well, all that diagram shows is you're doing rotating, which means the double bond's not moving at all. And does it actually move? No, it doesn't move. There is no double and no single bonds in the carbonate ion. All of the bonds are a little bit between a single and a double. That pair of electrons is kind of average in all three. How would we show that in Lewis structures? What we have to do is kind of modify this. In other words, we have to show which electrons are involved in the resonance. But before we do that, we have to agree that I'm going to need more than one structure. So let's imagine, if you will, that put the dots. Let's say I want to move that double bond to each one of the red on the left, just to keep it consistent with the book. And I say, okay, well, just show this double bond going here. You can't do that, because if you do that, now this oxygen has an expanded octet, which you can't have, right? And this one doesn't. This doesn't even have an octet. So it's a little trickier than just moving the line down. So let's imagine for this to become a double bond. Let's imagine that this pair of non-bonding electrons on the oxygen became bonding. In other words, it flipped in here. Now, if that goes there, this can't stay here because that gives the carbon 2, 4, 6, 8, 10. So if that pair of electrons becomes bonding, this pair of electrons is to become non-bonding. And that gives rise to resonance spectrum. Okay. So let's clean this up a little bit. So the days when I do stuff that isn't in the book, that's, as I told the students on Wednesday, that's not a good day to miss. We still have to keep the charge there. So let's do the same thing with the result of this occurrence. So now this oxygen is now stable. We didn't touch this. But now here, this oxygen only has 2 lone pairs on it. And where did that pair go? Now it's here. Okay. Notice that every oxygen single is associated with 8 electrons, 2.68, carbon 2.68. Except now the position of the double bond has moved. And by showing this, we're showing, no, it's not, we're not just turning it. We're actually moving the position of the double bond. Now we still got another position, it can go here. So by the same reasoning that we did over here. If we want to put the double bond there from here, then let's pick that pair of electrons. Let's pick that pair of electrons, and let's say that pair of electrons became bonding. And don't draw a solid line here, because you're saying the bond is above the bond. Draw a solid line that already has one. And if that flips in, then this can't stay where it is, because that gives this carbon 2, 4, 6, and 10. So that would mean that bond goes there. That would give rise to resonance structure. So this top oxygen was left untouched. It's still there. This oxygen now, though, has 2 lone pairs because it's part of the double bond now. And this one goes back to the way it was before. And you don't have to show this one going back and out. And again, it's important to kind of summarize here by going, none of these exist. There is never a double and 2 single bonds ever in carbon. All the bonds are a little bit between the single and the double. And that's common in chemistry where you've got single and double bonds next to each other. Whether it's got whether you've got a central atom or not, whether you've got an ion. And we're going to see a pretty important example that will do organic chem if we get to them. So how would this be worded on a test? Well, it'd probably be something like the carbonate ion can be represented by 3 resonance structures. Draw them, including the electrons involved in the resonance, which means these have to look like. And again, you just got to accept that none of these exist. This is just our way of showing that electrons are a little more elegant than just calling them dots and lines. Okay. And if you're interested, and I think I referred to this last time, is answering Patrick's question. When you say that something has an expanded octet, and can have an expanded octet because it has access to d orbitals, that probably means that d orbitals are involved in the bond. And then you need some pretty sophisticated bonding tools. And without going into it in any detail, the stuff written for AP, that line on left in there. If you go. And then it's yes. When we talk about hybrid orbital. If you go to page 351. We have my this one in charge, I'm probably gonna get you today on the page. I wanted to really if you look at the 1, 2, 3, 4, 5, 6, look at the top 6 columns. You see those little goofy things in the left-hand side, hybridization, SP, SP3, SP2, see that? What that means is the orbitals that we form in the molecule are combinations of S and P. Yeah. But S can only hold 6 electrons, or P can only hold 6, S can only hold 2. So when you have to blow up, you're never going to have anything with an 8. But if you have an expander, let's say you have 5 things around the central atom, and that's the next one. Notice it says SP. See that? Now imagine there's a 1 above the S and a 1 above the D. S1, 3, D1. 1 and 3 and 1 act as 5. So that's how many peripheral atoms there are, or what we call vertices. And it gets more complicated. But again, that's another way of looking at it. That's different than Vesper theory. But Vesper theory begs the question. I mean, how did d orbitals get involved in Gorn? Technically, they're not valence shelled, but if need be, they can be incorporated. And that's why we call it valence bond. And it's a very common one is what's called an sp3 hybrid. And when you look at the shapes of some of these things in section 6.5, you'll see that the shapes, p orbitals and s orbitals aren't facing in the right direction. So how can these shapes actually happen? And that's kind of the idea of hybridization. You guys have any words?
Thanks, staff and students. As a faith and learning community, let us prepare ourselves for the morning prayer.
Maybe I'll talk.
In the name of the Father, and Son, and the Holy Spirit. O God, we thank you for the life of Evan Rice. He opened his heart to Christ, present in those oppressed by poverty and injustice. May we follow his example of faith and generosity. Grant us the courage and compassion of Edmund as we seek to live lives of love and service. We ask this through Christ our Lord. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our heart. In the name of the Father, Son, and Holy Spirit. Amen.